We're going to introduce a topic now that is very important in helping us understand why it is that molecules interact with each other in the ways that they do. For example, we're familiar with the fact that if you take a teaspoon of sugar and place it into water and stir, the sugar readily dissolves in the water. They mix together and interact well. But if you took a tablespoon of oil and try to mix it into water, something totally different happens. The oil and the water do not mix together. They do not interact well. Instead, they push apart from each other. How can we explain, how can we understand what's happening here? And that answer lies in understanding polarity of molecules. In Chem 2A, this information is found in section 6.8 of your textbook. In Chem 22, it's found in section 10.8. It will be very useful at this point before you go any further if you have your textbook open and are looking at either table 6.17 or table 10.1, the same table that we were looking at when we were examining shape of molecules using the VSEPR theory. So if you don't have that table open, now would be a good time to do so. So what is a polar molecule? A polar molecule is a molecule in which one end of the molecule has a partially negative charge, and the other end of the molecule is partially positive. Now, we were looking at this idea of partial negative and partial positive points when we were discussing whether or not a bond was a polar covalent bond. We're taking that and now expanding the concept to the entire molecule, not just a bond between two atoms, but the overall entire molecule, right? If a molecule is a polar molecule, there is a net separation of charge over the entire molecule. One end of the molecule partially positive, the other end partially negative. So notice these two ends, that's linking us to the prefix di. These two ends acting like two poles here, a partial positive pole and a partial negative pole. There can be differences in the magnitude of the separation of charge, and this can be measured by something called a dipole moment. How big is this separation of charge? And the concept of dipole moment is explored further as you continue your studies in chemistry. I should mention here that not all molecules are polar. That's the point of what we're discussing at this moment. How can we determine whether a molecule is polar or not? If a molecule isn't polar, we refer to it as a nonpolar molecule, and it does not have a charge separation. In other words, if you look at the entire molecule, the centers of partial positive and partial negative charge are not separated from each other. Instead, they coincide at the same point, at the same spot in the molecule. Now, this is going to be an important set of criteria as we move ahead with this lecture. We want to be able to determine whether or not a molecule is polar or nonpolar. A molecule will be polar if two criteria. It contains polar covalent bonds. Now, we just explored the idea of polar covalent bonds. You have to look at the electronegativities of atoms involved in a bonding arrangement and see if the difference in electronegativity falls in the range of being at least 0.5 or greater, but less than 2.0. So a bond will be a polar covalent bond if its electronegativity difference falls in the range indicated. But that's not the only criteria. In addition, the molecule has to have a non-symmetrical shape. In other words, we have to examine and explore the shape of the molecule using the ideas we discussed with the VSEPR theory. If a molecule is a polar molecule, Note that it will be very interested in attracting to other polar molecules. It will attract to molecules that are identical to itself, and it will also attract to different but other polar molecules. So I've given a little schematic here, right, just in general representing a polar molecule with this oblong shape and noting the charge separation in the molecule. One end is partially negative, the other end is partially positive. So here is polar molecule number 1. Right, here is a second polar molecule, either identical to number 1 or a different but polar molecule. And you can see here that electrostatic forces of attraction will apply whenever there is opposite charge interaction. So if this partial negative end of this one molecule is in close contact with the partial positive end of a second molecule, then they're going to experience attraction for each other, and they're going to want to stick together. So that's a key idea in understanding why it is that things interact well with each other. If they can form this polar attraction due to their partial charges being opposite but in close contact. Let's take a look at several different examples of molecules and determine whether or not the molecule is polar or nonpolar. So the first example that I'd like to look at with you is the molecule methane. Now we can quickly draw the Lewis structure for methane using the steps that we've explored in previous lectures. And if we do that, we come up with this Lewis structure for the methane molecule. But we know from exploring VSEPR ideas that methane is not a flat molecule. It doesn't have bond angles of 90 degrees. Instead, as we look and we see that there are 4 groups of electrons around the methane molecule, reminding ourselves of the information that's found on table 6.17 or table 10.1, we know that those 4 electron groups are going to want to repel away from each other and get as far apart as possible. So if we have 4 bonding electron groups, then we know that the geometry of that molecule is going to be tetrahedral. So if we have 4 electron groups around a central atom, the geometry tetrahedral, and we can redraw methane showing what its shape actually looks like. So I'm drawing this tetrahedral shape around the carbon atom assumed by the electron pairs repelling as far apart from each other as possible. We know that if the geometry is tetrahedral, the bond angles are 109.5 degrees, and we can put that under the bond angles. And now it's an important point to think about what the actual molecular geometry is for the molecule. Now the molecular geometry is different from the electron pair geometry in certain circumstances. It depends on whether or not any of the electron groups around the central atom are lone pairs or bonding pairs involved in a bond with another atom. When you look at the molecular geometry, the only thing that shows up in the quote picture of the molecule are actually the nuclei themselves. The electrons are not dense enough to quote get their picture taken. So when you look at the molecular geometry, you're looking at the atoms themselves and their nuclei that have enough density to basically be observed in a picture. So examining the structure of methane, we see that all 4 electron groups are involved with bonds to other atoms. So in this instance, since all 4 electron groups are involved in bonds, the actual shape of the molecule is identical to the electron group shape, and we say that the geometry is tetrahedral as well for the molecule. So tetrahedral geometry. Now that we have filled in all of this information, we're ready to examine the polarity of the molecule. Is methane a polar or a nonpolar molecule? But what do we have to look at? What do we have to consider? First of all, does it have polar covalent bonds? And how do we do that? How do we answer that question? We look at the electronegativities of the atoms involved in the bonds. Carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1. And the difference in that electronegativity is 0.4, which is not exactly falling into the polar covalent bond range. So you could make an argument that methane is not a polar molecule because it does not have polar covalent bonds. But as I said, this range of electronegativities can have some fluctuation, and some individuals might make the case that yes, there is some polarity here. So let's just go ahead and examine the second criteria if you did want to make the argument that the bonds were polar covalent bonds. Let's take a look at the second point. Does methane have a non-symmetrical shape? Now, this idea of symmetry is something that takes practice in visualizing and seeing. But let's see if we can't understand by looking at this molecule. If we were making the argument that carbon was the more electronegative atom, then carbon would have a partial negative charge here, and each hydrogen would be slightly partially positive. So again, partial negative spot here, and each of the hydrogens partially positive. Well, where would the center of partial negative charge be if carbon was the only atom that was partially negative? Well, it would have to be right here on the carbon atom. Where would the center of partial positive charge have to be if each of the hydrogens was partially positive? All right, so the center of partial positive, this idea like a center of gravity, what point would you locate where you're sort of equidistant between all of the partial positive charges? So if you have partial positive here and here and here and here, the center of partial positive would also have to be right on the carbon. So if I'm pointing to carbon as the center of partial negative charge, but also pointing to the carbon as the center of partial positive charge, then there is no charge separation within the methane molecule. There is not one end that's partially negative and a separate end a distance away that's partially positive. There is no uneven charge separation. The center of partial negative and the center of partial positive charges reside in the same spot on the carbon atom. So we're going to indicate here that methane is a nonpolar molecule. A nonpolar molecule. And the key reason for that is because it has a symmetrical shape. It is not a non-symmetrical molecule. it has a symmetrical shape, therefore the partial positive and partial negative charges coincide. Right? So centers of partial positive and partial negative coincide. It does not have a charge separation over its entire structure. So that's our first example, the methane molecule. Let's take a look at a second example, and this is the molecule ammonia. So while I am erasing the board, you can perhaps quickly draw the Lewis structure for the ammonia molecule. What does this molecule look like? And if you draw the Lewis structure for the ammonia molecule, you'll see that nitrogen is central, the 3 hydrogens are bonded to it, and there is a lone electron pair or unshared electron pair on the nitrogen as well. So we have 3 bonding electron groups, and we have 1 lone electron group, which gives us a total of 4 electron groups. However, it's a little different situation than methane in that one of these electron groups is a lone electron group. But the electron shape is determined just by the total number of electrons. So whenever you know that you have 4 electron groups, regardless of whether or not they're bonding groups or lone groups, those electrons will repel each other and push as far away as possible. So they are going to assume a tetrahedral shape. And we can draw the structure of ammonia showing that tetrahedral shape that the electron groups are assuming. So here is my lone electron pair, and then these remaining electron groups are bonding groups involved in a bond between nitrogen and hydrogen. So our electron shape is tetrahedral because we have 4 electron groups. The bond angle is also 109.5 degrees. Whenever you have an electron group geometry that is tetrahedral, bond angles will be 109.5. Looking at the molecular geometry for ammonia, and here is a model of ammonia. Blue is nitrogen, and the white balls are hydrogen. So here is our lone electron group, not involved in a bond, and our 3 bonding electron groups. Now you remember that I said that when you're looking at the shape of the molecule, the lone electron group does not have enough density to essentially get its picture taken. So if you look at a picture of ammonia, you're going to see a point for the nitrogen nucleus and then points for each of the hydrogen nuclei. And we're trying to describe what sort of shape does the molecule itself have, right? The atoms in it. And if you take a look on the tables, either 6.17 or 10.1, you see that whenever there's a situation where there are 4 electron groups, but 3 are bonding groups and 1 is a lone electron group, the term we give for the molecular geometry is trigonal pyramidal. Trigonal pyramidal. And that's just a description coming from what we see when we look at the molecule. It looks like a pyramid with a 3-point base. Now we need all of this information to get to this last and very important question. Is ammonia a polar or a nonpolar molecule? Well, how do we answer that question? Right back to the two criteria. Does it have polar covalent bonds? And does it have a non-symmetrical shape? Well, looking at the electronegativity values to understand whether it has polar covalent bonds, you remember that nitrogen has an electronegativity of 3.0 and hydrogen an electronegativity of 2.1. So if we consider the difference in electronegativity between nitrogen and hydrogen, that electronegativity difference is 0.9. And that's placing it clearly in the category of polar covalent bonds. What that means is that we can go back and now indicate, and I'm going to remove the bond angle here from the picture just to keep it a little less cluttered, right? We can now go back and indicate that nitrogen must have a partial negative charge because it's attracting those shared electrons more closely to its own nucleus. And each of the hydrogens is partially positively charged. So, looking at the model, partial negative on the nitrogen and partial positive, partial positive, partial positive on each of the hydrogens. Where is the center of partial negative charge? Clearly, it's resting on the nitrogen. Where is the center of partial positive charge? Well, if we have partial positive charge here and here and here, the center of partial positive charge must be in the plane formed by these hydrogen atoms and right in the midpoint of it. So right about here. So notice my finger. Partial negative center is right here, but I'm having to move to get to the center of partial positive charge. As soon as you are looking at a situation like that, the molecule is a polar molecule. It's meeting the criteria that we said when we introduced the concept. This end of the ammonia molecule is partially negative, where the nitrogen atom is, and it will be interested in interacting with any other center of partial positive on a separate molecule. This end of the ammonia molecule where the hydrogens are located is partially positive, and it will be interested in interacting with the center of partial negative charge on another polar molecule. So ammonia is very directional in its orientation of how it wants to interact with other molecules because it is a polar molecule. So we can say here that ammonia is polar. It's a polar molecule because it has, and I'm abbreviating here, polar covalent bonds. It has polar covalent bonds, and it is not symmetrical. It is not symmetrical. Therefore, its centers of partial negative and partial positive charge are separated in the molecule. Let's do one more example to illustrate this concept, and that is water, a very important molecule. So while I am erasing the board, you can quickly draw the Lewis dot structure for water. Lewis dot structure for water. And if we look at that Lewis structure for water, we see a structure that is written by beginning chemistry students most often like this, right? Water being shown in a linear shape. But now that we understand VSEPR, we can evaluate and see that this drawing is in fact not the correct shape for water molecules. I see that water has two bonding electron groups and two lone electron groups, and that adds up to a total of 4 electron groups. Now, whenever you have 4 electron groups, you know that the electron geometry has to be tetrahedral. Those electron groups are going to push as far apart from each other as possible. So if I draw water indicating in fact what its shape looks like, I'm going to have a structure that looks like this. Let me pull up my model of water here for you to look at, right? We see that we have 2 lone electron groups, and then we have 2 bonding electron groups, but those total of 4 electron groups assume the same tetrahedral shape that we've seen in both methane and ammonia. We know that bond angles here are 109.5. You see those bond angles whenever the electron geometry is tetrahedral. What does the molecular geometry look like for the molecule? Well, again, the lone electron pairs are there repelling, but they don't have enough density to actually get their photo taken if you took a picture of the molecule. Instead, you would see a point where the nucleus of this hydrogen and this oxygen are located. And what descriptive term do we give to the shape of the molecule? Well, you can see on the table that we give the term bent for the molecular shape, which is a pretty good descriptor of the actual shape of the molecule. All of this information now enables us to evaluate whether or not water is a polar or a nonpolar molecule. So looking at the water molecule, where is the center? Well, before I get to that, backing up, we have to consider, first of all, whether or not there are polar covalent bonds present in the water molecule. That is always the first thing we have to look at. So looking at the oxygen atom, it has an electronegativity of 3.5. The hydrogen atoms, again, have electronegativity of 2.1. So if we consider the difference in electronegativity, that difference is a value of 1.4, which means that the bond between hydrogen and oxygen is quite polar, falling very solidly in this range of polar covalent bonds. Therefore, oxygen is pulling those shared electrons more closely to its nucleus and has a partial negative charge, and each of the hydrogens is partial positive. So with that information, we're now ready to take a look at the shape of the molecule, understanding where partial charges are, and evaluate whether or not the overall water molecule is polar. Is it a dipole? So it has polar covalent bonds. What's the situation with its shape? Well, its shape is bent. That means the center of partial negative charge is on the oxygen. We have partial positive charge on each of the hydrogen atoms. Where would the center of partial positive be? Well, it would have to be halfway between the line connecting the two atoms. So partial positive charge here, partial positive charge here. The center of partial positive right at the midpoint between the two atoms. So partial negative charge on the oxygen, and I'm having to move my finger to get to the center of partial positive charge. We're looking at a dipole. We're looking at a charge separation. Water is a polar molecule. This end of the water molecule is where the center of partial negative charge is residing, and this end of the water molecule, midpoint between the hydrogens, is where the center of partial positive charge is. So water is a polar molecule. It has polar covalent bonds, and it is a non-symmetrical molecule. It is a non-symmetrical molecule. It meets both of the criterias, and it is a polar molecule.